Hello everyone, welcome to this session, Acceleration Analysis in Mechanisms using Graphical Vector Approach. In the previous session, we discussed the acceleration analysis of a point on a link, and we observed that the acceleration of a point, it can be divided into two components. One is the tangential acceleration component and another is the centripetal acceleration component. In this session, we will take up a numerical problem related to acceleration analysis of a Fourbar mechanism, and we will see how can we apply the concepts learned in the previous session to calculate the acceleration of different points in the Fourbar mechanism. So let us begin with the numerical problem. So let me read out the numerical problem for you. So we have been given a Fourbar mechanism as shown in the diagram. So in this Fourbar mechanism, the length of the links are given as AB equal to 50 mm, BC equal to 66 mm, AD is equal to 100 mm and CD equal to 56 mm. The link AB rotates with an instantaneous angular velocity of 10.5 radian per second and an angular retardation of 26 radian per second square in the counterclockwise direction. Now let us see what we need to find out. So first we need to determine the linear acceleration of the point C. Then next we need to determine the linear acceleration of point E, that means this point, given BE is equal to 40 mm. Next we need to determine the linear acceleration of the point F, given BF is equal to 45 mm and CF equal to 30 mm. Finally, we need to calculate the angular acceleration of the links BC and CD. Just to mention here that the Fourbar mechanism shown in the diagram here is similar to the Fourbar mechanism we considered during the velocity analysis. Now let us see what are the different steps for acceleration analysis in this Fourbar mechanism. So obviously the first step is to draw the configuration diagram for the Fourbar mechanism. So this thing we have already discussed in the previous sessions, that how can we draw the configuration diagram using the length of the links and the angle which these links they are making with the fixed link. Afterwards, the next step is to draw the velocity vector diagram for this Fourbar mechanism. So the velocity vector diagram, this thing we have already discussed in the previous sessions, that the velocity vector diagram, it can be produced something like this, right? So this part since we have already covered in the previous session, so I am not going to discuss it again. Just remember that the Fourbar mechanism, right, which is shown here, it is identical to what we considered during the velocity analysis and mechanisms. Now let us directly go to the acceleration analysis part so that we can have a better understanding of the acceleration analysis and mechanisms. So obviously the next step is to write down the vector equations for point C. So here basically we are targeting to calculate the linear acceleration of point C. So we will start with writing down the vector equations for point C. So obviously the vector equation for point C, it will be given something like this. So see, this expression, it is almost identical to what we considered for the velocity vectors. So this will be given as FCA vector, that is acceleration of C relative to A, is equal to FCB, that is acceleration of C relative to B, plus acceleration of B relative to A. So FCA vector is equal to FCB vector plus FBA vector. Now the only difference, right, in the velocity vector equation and the acceleration vector equation is that right now we will have two components for each of the acceleration vectors, right? So let me again modify this equation first like something like this. That is this FCA vector. Right now it will be replaced by this FCD vector, that is acceleration of C relative to D. So this is because of that both again the points A and D are fixed points, right? So it doesn't matter whether you write it FCA vector or FCD vector. Now this will be again equal to, right, now you just rearrange these two vectors, that is FBA vector plus FCB vector. Afterwards you break down all these vectors into two components, that is the centripetal and tangential component. So right now FCD vector you can write down as FCD C vector, FCD T vector, and again equal to FBA C vector plus FBA T vector. Similarly you can break down this FCB also into two components, so it will become FCB C vector plus FCB T vector. Now let us move ahead. So afterwards we all know that the next step is to quickly run a magnitude and direction analysis. So right now see, just one point to mention here is that initially when you're starting with the acceleration analysis or velocity analysis of mechanisms, it is always better to write down the vector equations, right? However, once you become habitual, once you have a good amount of practice for this, then you can ignore writing down the vector equations, and then you can directly basically mark the vectors which are known and unknown and start with the acceleration vector diagram. But initially it is suggested that you use this approach, right, to draw the acceleration vector diagram. Now let's move ahead. After this we are going to run a magnitude and direction analysis, but here, right, so as compared to the velocity vector equations, a number of vectors are involved. So basically we will be drawing a table, right, to run this magnitude and direction analysis. So we will start with the vectors which are completely known in magnitude and direction. So obviously, as we know, the angular speed omega of this link is given, and at the same time the angular acceleration of this link AB, input link AB, it is given to us. So we are going to start with the vector FBA, correct? So now the first vector which will be write down in the table will be FBAC, right? And then let us see what is the magnitude of this vector. So see, this is the sequence which you should follow while conducting the acceleration analysis. That is, first the configuration diagram, then the velocity vector diagram, and finally the acceleration vector diagram. Now once you have the velocity vector diagram, you can easily calculate the magnitude of centripetal component. So from the velocity vector diagram we can obviously measure the velocity of point B relative to A, which is given by AB vector, correct? And then we can calculate its magnitude something like this. So the magnitude of this FBAC, it is given by 0.525 square divided by 0.05, that is equal to 5.51 meter per second square. And again the direction of this FBAC vector will be from B towards A, right? So this is the centripetal component, so it's very obvious that it will be from B towards A and again parallel to AB, right? So let us mark all these things, right, into this table, right, one by one. So this is nothing, this is what we did for the velocity analysis. We are simply running a magnitude and direction analysis here also. Now let us move to the next vector. So the next vector is obviously this one, the tangential component of FBA. So let us write it down. So FBA T is equal to, right, let us check the magnitude of this vector. This FBA T is equal to alpha AB, right? So as we discussed in the previous session, that the tangential acceleration component, it will be given by the length of the link multiplied by the angular acceleration of the link. So now alpha is provided to us, correct, in the length AB is known to us, so we can calculate this component. So this will be basically 26 multiplied by 0.05 equal to 1.3 meter per second square. Now this component, this tangential component, we know that it is perpendicular to AB, correct, perpendicular to this length AB, right? And what is the sense? Now here one thing is very important, right? The sense of this vector, it will be basically towards the right hand side. What is the reason? Because see, although we know that the link, it is rotating in counterclockwise direction, but right now we have been given an angular retardation of 26 radian per second square. So the direction we are going to take it in the opposite sense, that means like opposite to the counterclockwise direction. So this acceleration, it will be basically pointing towards the right hand side. Now let us move ahead, and again let us see the next vector. So the next vector in this table will be obviously FCBC, that is the acceleration of C relative to B in the centripetal component of this acceleration vector. So let us check the magnitude of this vector. So obviously the centripetal components, once we have drawn the velocity vector diagram, the centripetal components, they are all known to us. Just keep this thing in mind. So here again the centripetal component, it will be calculated as BC square divided by BC. So again this BC square is nothing, this is velocity of C relative to B. So let us measure this BC length from the velocity vector diagram, and then let's just substitute those values here. So it can be written down something like this, that is 0.35 square divided by 0.066, that is equal to 1.85 meter per second square. Now again this acceleration vector, right, the direction will be what? Since it's a centripetal component, it will be parallel to BC. And what will be the sense? The sense will be basically from C towards B, right? Now just let me take you back to the vector equation. So just remember, right, I am just following, right, the vectors in this vector equation one by one. So I am just writing down these vectors right here in the table one by one, and then I am just checking their magnitude and direction, right? So I am just marking all those things into this table. Now this is done. Then let's come to the next component, which is FCB tangential. So let us come to this FCB tangential component. So obviously right now we don't have any idea about the angular acceleration of link BC. So FCBT component is right now unknown to us, and also with the given data in the numerical problem, it is not possible to calculate FCBT. So right now we don't know the magnitude of this vector, but do we know the direction? So the answer is yes, the direction is known to us. We know that this is the tangential component and it will be perpendicular to BC, right? But do we know the sense? Let's come to this question. So obviously right now we don't know the sense, that this vector, it will be, let's say, pointing to upward, downward, towards left or towards right, right? So now let us mark this thing, that sense is not known to us. So we will simply put a cross sign in the table, right? Now again let's move to the last vector. So obviously the last vector which is right now left is this one, these two vectors, that is acceleration of C relative to T. So let's go to each of these vectors one by one. So again FCDC, so do we know the magnitude? Obviously we have the velocity vector diagram, so we can directly calculate the magnitude of centripetal component of C relative to D, correct? So now let us see the magnitude. So the magnitude is simply given by, right, velocity of C relative to D divided by the length DC. So this DC square we can measure basically from the velocity vector diagram, and we can calculate this magnitude as 0.43 square divided by 0.056 equal to 3.3 meter per second square. Now again, if you carefully observe that right now the direction of this will be parallel to DC, and the sense will be from C towards D. So just remember, right now we are saying acceleration of C relative to D, right? So this will be obviously from C towards D. Now let us move to the last one. The last vector is again FCDT. So again the question arises here, do we know the magnitude of this vector? So the answer is no, because right now we don't have any idea about the angular acceleration of link CD. So alpha is not known, so that's why it is not possible to calculate the tangential acceleration component for this vector. But do we know the direction? So yes, the direction is known. So the direction of this vector, it is perpendicular to DC, right? So do we know the sense? Obviously the sense is not known. Again, we don't know anything whether this vector is pointing downward, upward, left side or right hand side, right? So again, the sense is not known to us. So let us mark the cross sign into the table corresponding to this vector, right? Now after this, after keeping all these vectors in the table and quickly running the magnitude and direction analysis, next what we are going to do, next we are simply going to draw the acceleration vector diagram, keeping in mind that we will start with the first vector in the table, then we will go to the next vector and so on. So let us start with this thing. So first we are obviously going to draw the vector diagram for point C, right? So again, first we are going to mark the pole point A1D1, right? So A1D1 pole point we have marked here. Then next we are going to draw the first vector FBAC and FBAT, right? So let us draw these two vectors first. So these are right now completely known in magnitude as well as direction. So let us draw these two vectors. So this is basically FBAC, right? And then finally this is your FBAT, correct? And so just remember here, so right now I am choosing simply a scale of 1 centimeter equal to 1 meter per second square to draw these vectors. So now after this, let us draw another vector in the table. So obviously the third vector in the table is the FCBC vector. So we know FCBC is right now, right, parallel to this length BC, correct? And again FCBC, it will be drawn something like this. So let us complete this FBA vector first. So this is your FBA here, and then finally this is your FCBC. So again, just see here, right, we are simply using the head to tail approach to draw the next vector. So here we know that A1 B1, this is representing the acceleration of B relative to A. So FCB, that is acceleration of C relative to B, obviously the tail point of this vector is this point B, so it is going to start from this particular point. So FCBC is from C towards B, starting from this point B1, right? Now let's go to the next vector, that is FCBT. So we know that right now the magnitude of this vector is not known to us. So what we are going to do, we will simply draw a line perpendicular to length BC, right, through this point CB to represent the direction of FCBT, right? So right now we are simply drawing the direction of this vector, right? We don't care about magnitude. So what we are going to do, we will take a line of any arbitrary length and we will draw a line perpendicular to BC, obviously through this point CB, right? So obviously the tangential and the centripetal component, they are meeting at this intermediate point, at this common point. So the FCBT component, it will start with this particular point CB, right? Now this is your FCBT. Now let's move to the next vector, which is FCDC. So again FCDC, you see here the tail point of this vector is basically point D, and this point we have already located in the acceleration vector diagram with this D1 notation. Now what we are going to do, through this point D1 we will draw a line parallel to CD, right? And again we will take the magnitude what we showed in the table, right? So now let us draw this FCDC component. So FCDC component, once we have drawn, right, so you can check it out here. Then now let us move to the next component. The next component is FCDT. Now again, very important, right? We don't know anything about the magnitude of FCDT, so we will simply draw the direction of FCDT. So to draw the direction of FCDT, we will start with the point, right, where this acceleration F component FCDC is ending. So basically we are going to start with this point. So now let me draw this FCDT. So through FCDT we are again going to draw a line perpendicular to length CD, right? So let me draw the line first. So this is that line. Now this thing is very obvious that these 2 points, they are going to intersect at the common point, which is the head point C, right? So you can very carefully observe here that right now the common point to these two acceleration vectors, right, or you can simply say the head of these two acceleration vectors, it is given by point C, right? So now you can carefully observe, right, the letter which is common to these two vectors. This is basically this letter C, and obviously C is representing the head of these two vectors FCBT and FCDT, correct? So obviously the intersection of these two lines, right, these two blue lines, this is going to give you the point C, right? Or you can simply say, right, to differentiate it from the velocity vector diagram, you can mark this point as C1. However, right, for convenience, you can go in a similar way. You can simply remove this subscript. So obviously this is according to your convenience, what suits to you, right? So now let us move ahead. Once you get the intersection point, it becomes very easy to calculate the linear acceleration of point C. So if you remember, that was our objective, to calculate the linear acceleration of point C, which is given by FCA vector. Now to calculate this FCA vector, you simply join this A1C1 line. So once you join this A1C1 line, measure this length A1C1, and after measuring this length, this is going to give you 6.5 centimeter, that is equal to 6.5 meter per second square, right? So this is very easy, right? So certain things which you need to keep in mind is, let's say wherever you are getting the completitude, magnitude and complete direction of the vector, you draw it completely. Wherever you are getting only the direction of that vector, you can simply draw a line of arbitrary length to represent that particular vector, right? And again, while drawing these vectors, you follow the sequence in the table, correct? So that is somehow very fruitful, right, in approaching such kind of numerical problems, right? Now let's move to the second part. So the second part is obviously to calculate the acceleration of this point E relative to B. So to calculate this, what we are going to do, we will simply draw the vector diagram for point T. Now this is again very easy. So in this case again, we are going to mark a point E1 on vector B1 C1, that is acceleration of C relative to B. So the acceleration of C relative to B, it is simply given by this line, right, B1 C1. Join these two points with a solid line, right, and you can represent this vector B1 C1. Now here we know that this B1 E1, right, divided by B1 C1, it should be equal to BE by BC, right? So this is exactly identical to what we did in case of a velocity vector diagram, right? So now we will calculate this B1 E1 distance, right? From here, first we will measure B1 C1, which will give us 2.2 centimeter. After that, we will measure B1 E1, which is going to give us 1.33 centimeter. So using this length, we will mark the point E1 somewhere here, right? And once you have marked this point E1, to calculate the acceleration of this of intermediate point E, right, you can simply join A1 E1, just measure this length A1 E1. So this is going to give you 6.2 centimeter, and again you convert it to a proper scale. So the absolute acceleration of E, this is equal to length A1 E1, and this is going to give you 6.2 meter per second square, right? Now let's go to the next part, which is calculating the acceleration of this offset point F. So to calculate the acceleration of this offset point F, we are again going to follow the acceleration image concept, right? So we know that right now the triangle B1 C1 F1, it should be similar to triangle BCF to locate the point F, right? So the smaller triangle B1 C1 F1 is a triangle in the acceleration vector diagram, and the capital triangle, the larger triangle, triangle BCF, it is the triangle in the configuration diagram. So these two triangles should be similar. So from here we conclude that B1 F1 divided by B1 C1, this is equal to BF by BC, and C1 F1 divided by B1 C1 equal to CF by BC. From here you just calculate the lengths B1 F1 as 1.5 centimeter, because we have already measured this length from the vector diagram, right? So this, you know, this is 2.2 centimeter, something like this. Then you just substitute the values of BF BC here, and you calculate this length B1 F1 as 1.5 5 centimeter, and then again you calculate this length C1 F1 as 1.0 centimeter. Now after calculating this length, again see the tail of these two vectors, it is already located in the vector diagram, right? So B1 C1 we already have in the vector diagram. This is our B1, and then again this is our point C1. So what we need to do, we simply need to locate the head of these two vectors. So the head of these two vectors is the common letter F1, right? So what we are going to do, first we will take the point B1, then we will draw an arc of length 1.5 centimeter. Then next we are going to take the point C1, right, as a center, and then we will again draw an arc of length C1 F1 equal to 1 centimeter. Now the intersection of these two is going to give us this point F1 in the acceleration vector diagram. So once you have this point F1 in the acceleration vector diagram, to measure the acceleration of this offset point F, you join this A1 with this point F1, right, and just measure this length. So from here we just measured this length and we got the value of 5.6 meter per second square, right? So this is how we are going to calculate the acceleration of intermediate point as well as the acceleration of offset points, right? So just see here that right now the process to calculate the acceleration of intermediate and offset points, it is almost identical to what we did in case of velocity vector diagrams, right? Now let us come to this, how to calculate the angular links of BC and CD. So again, this is very easy, right? So FCBT component you have already known, right? So we know that acceleration component, the tangential component, it is given by simply R alpha. So we already know the FCBT component, so we can measure this length CBC1, right? So this component you can see here. So you can measure this component CBC1. So alpha CB, it will be simply FCBT divided by CB, right? So this is going to give us 1.8 divided by 0.066 equal to 27.7 radian per second square, right? Now the direction of this, obviously you can figure out by the direction of this vector, and now this is going to give you a counterclockwise direction, right? Now let's move to the angular acceleration of length CD. So again FCDT, that is the tangential component of FCD vector. So the tangential component you have already calculated. So this is your FCDT. So measure the length of FCDT, right? So just put the length here, right, and in the end you will get a value of 101.79 radian per second square. And again you can see from this diagram, right, so this vector, it is pointing in the downward direction. So obviously the direction of rotation of this link CD, it will be counterclockwise. So in both the cases the direction of rotation of links will be counterclockwise, right? Now let me again quickly summarize this for you, right? So what were the different steps for acceleration analysis in the Fourbar mechanism? The first step is to draw the configuration diagram. The next step is to draw the velocity vector diagram. And again the next step is to write down the vector equation. And again the next step is to break down each vector in the vector equation into two components. And finally you quickly run a magnitude and direction analysis. You prepare a complete table, right? Mark each vector in the vector equation in that table, check their magnitude and direction, right? Now while drawing the acceleration vector diagram, just remember this point, right? Start with the first vector in the table, the vector which is obviously completely known in magnitude and direction, then go to the next vector, then go to the next vector, and so on, right? Now here just keep in mind, right, wherever you have complete magnitude and direction, you draw that vector completely, and wherever you have the direction, you represent that vector with a line of some arbitrary magnitude, right? Now this was the entire summary of basically acceleration analysis of Fourbar mechanisms. Now the similar approach, the similar concepts you can extend to acceleration analysis of multi-link mechanisms also. So with this I would like to conclude this session, and in the next session we will take up another numerical problem consisting of 6 links. So see you in the next session. Thank you.